Good afternoon, people, and welcome to an exciting episode of I Don't Get It. You are going to need the diagnostic topic test, if I can say it. You're going to need that in front of you for this, and probably your answers in front of you for this, because I'm going to go through every single question that you've asked me to go through on this video. So pause the video now if you need to go and get them, and I'll wait for you. All right, let's get a start. Nobody asked me about question 1. That seems to be taken care of. But question 2, question 2D, a lot of people ask me about. Hang on a second. Greater presentation. High production values here, my friends. All right, question 2D. This is about the lightning bolt question. It said calculate the total number of joules carried by this lightning bolt. Now, at this stage, by the time you've done A, B, and C, you already know quite a bit, right? The question told you that the current was 200,000 amps, and it told you that the voltage was 1.2 million volts, and it told you that the time was 0.01 seconds, and it told you that the total charge was 2,000 coulombs. Now, it's very handy to firstly write down this list, right, at the start of a question before you start trying any calculations. But it's also handy to put all of these numbers in the correct units, right? That was given in I think kiloamps, and that was given in megavolts, and that was given in milliseconds, etc. But you're not going to put the numbers in like that. They have to go into a formula in amps and volts and seconds. So just convert them straight away. Right? Get it out of the way, write them down the way they're going to be, and you won't mistakenly put the wrong number in a formula later in this question, okay? So we've got all that. And this question said, find the total number of joules in this lightning bolt. Here's the answer. Joules is the unit of energy. So if anything ever asks you for joules, it's either energy or work done, because they're both measured in joules. Nothing else is. So you find the energy formula. Right? That there is the energy formula, the specific formula for electrical energy, voltage times current times time. We've got all of those in the list up here. Right, easy. So throw the numbers in and get the answer. But again, it's important that you get the right numbers. Right? A lot of people told me that they got that answer, but they didn't get the 9. Right? And that's almost certainly because of a metric conversion problem, that you either didn't do it or you converted it differently. Right? So that's the answer, my friends. Okay, 2E. It says calculate the total power in the lightning bolt. All right, 2E is up here. Formula for power, pretty easy. P equals VI. Power, by the way, is the rate of use of energy, right? It's always energy divided by time. So if you look at the energy formula, right, VIT, if you divide that by time, that just gets rid of this, right? So power is VI. That's where this comes from, right? So V times I, there it is, 2.4 by 10 to the 11 watts. And again, a few people said they were out by a factor of 100 or 1,000 or something, and that's probably a metric conversion problem. All right. I know. 2F. I like 2F. This is a question that asks you to explain something, which is why people have trouble with it, because most people who can do calculations have trouble explaining things. So it says, explain why this form of electrical energy has not been used for domestic houses. All right. Why don't we use lightning bolts to supply our electricity? Right. Rightio. One thing about this question, wherever it says explain, it has a specific meaning. Right. When you explain something, you have to link the cause and the effect. Right. This is your job here. They nearly always put the effect in the question. Right. This is the effect. Right. The effect is lightning bolts don't get used to supply our electricity. Right. What's the cause of that? What are the causes? What are the reasons that we have that effect? We have to get our electricity somewhere else. Right? So we've got to do this bit. Well, part of me just wants to say that, but then I've reminded myself that I want to get some marks. So here are the answers. There's quite a few. You can pick any 2. It was worth 2 marks, so come up with 2 reasons. I reckon there are 3. Here they are. Firstly, it's unpredictable. You've got no idea where or when a lightning bolt will strike. Right? Secondly, it's uncontainable. Even if it does strike, it tends to destroy things. Right? It blows trees out of the ground. Right? It will also melt any power line. That much current, what was it, 200,000 amps? There is no power line in the world that can handle 200,000 amps. Right? They can handle 3 or 4 or 500,000 volts. Right? But as long as the current is tiny, it can do that. Right? That many electrons, keep in mind, current is the amount of electrons passing a point in 1 second. Right? That many electrons, that's the end of it. That'll melt anything. So we can't contain it. We can't transport that electricity. Right? And it's also dangerous. Right? That much voltage can jump, well, like lightning. Right? Even if we could run that sort of voltage and that sort of ampage down a power line, it would just lightning bolt itself across to the next power line, or it would lightning bolt itself down to the car that's driving under the power line, and it would kill people. Right? So it's unpredictable, it's uncontainable, and it's dangerous. Plenty of reasons not to. So they're the answers. Any two of those would be fine. All right. I'm going to skip to question 4 now. So just get question 4 in front of you, have a read of it. Pause the video if you need to, but I've got question 4 here. And the reason I've done this instead of drawing it myself is because I'm too lazy to reproduce this graph, and I'm probably not good enough to do it this accurately. Pardon me. Now you know it's me. Okay, it says, Figure 3 shows a voltage current graph for a particular electrical device. So before you even read the questions, when you look at a graph, when you get a graph in a question, have a good look at the graph and sort of understand what it's showing you, right? That's voltage, that's current, right? So there's some electrical device, right? So this is like a hairdryer or something, or a ceiling fan. It's a device that uses electricity. So something that uses electricity, when it's got 1 amp going through it, it has 10 volts across it. When it has 2 amps going through it, it's got what? 14 volts across it, okay? So the more current goes into this device, the more voltage it uses as well, right? And vice versa. All right, clearly that depends on that, because that's how graphs always go. That's always the dependent variable, that's the independent variable. So now we sort of understand the graph a little bit more. Don't just go straight past the graph, read the question. You'll only have to go back and do that again. So know the graph first, right? Okay. Is this thing ohmic or non-ohmic? What the hell is that? All right. I'm going to come back to this in a second, but I'm going to show you what ohmic and non-ohmic means. V equals IR. This is called Ohm's law. Right? You don't need to know why it's named after a guy called Ohm, right? And resistance is in ohms. Now anything that conforms to this at any voltage and at any current is an ohmic device. For example, the resistance of anything is pretty constant, right? The resistance of an ohmic device is pretty constant. So if a light globe has a resistance of 3 ohms, it's got a resistance of 3 ohms if 1 amp of current is going through it, or if 2 amps or 3 amps or 5 amps or 10 amps or 100, right? The resistance doesn't change, right? So if you rejig this, if you rejuggle this, you get R equals V divided by I, right? And if that's constant, and if that doesn't change, and most things have a constant resistance, that's an ohmic device, right? And if that doesn't change, that ratio doesn't change. And V divided by I would be the gradient of a voltage versus current graph. Making sense? An ohmic device has a constant resistance, and because this formula is literally in the form y equals mx plus c, right? That's always going to make a straight line if one of those is constant, right? And of course, this is how you find the gradient, rise over the run. So an ohmic device would get you a straight line on a V versus I graph, because the ratio of V to I would have to be the same, because that's the resistance. Ohmic devices have a constant resistance. Right, let's have a look at the graph that we've got. Not ohmic. This is making a curve. That is not an ohmic device. So all you've got to say in the answer is, firstly, answer the question, is it an ohmic device? No, it's not. So you say non-ohmic, right? Non-ohmic. There you go. And then say why, right? You can either say the resistance is not is not constant, if I can get the word out, or you can say the graph is not a straight line, or you can say the ratio of voltage to current is not constant. Either way, right? So somehow you have to say that R equals V divided by I is not going to get you the same R no matter where you go, right? That voltage divided by that current is not going to be the same as that voltage divided by that current because it's not a straight line, non-ohmic. There you go. Now you know. Part B. Which one of the following statements is true about a device whose graph is shown? Okay. Its resistance is constant. Well, we just said it isn't constant. Can't be that. Its resistance increases as the current increases. Let's check it out. Resistance is voltage divided by current, right? So let's just try it. If that's 10, that's 4 volts, and that's 0.2. So 4 divided by 0.2 is 20. So the resistance at that point is 20. I'm making a real mess of this graph. Here's another one. That's 10 and that's 1. 10 divided by 1, voltage divided by current, is 10. So the resistance at that point is 10. So does the resistance increase as the current increases? No, it's going down. Started at 20. As we increase the current, it's going down to 10. So that's garbage. Its resistance decreases as the current increases. Yep, we just figured that out. That's it. Don't even have to read that. Okay. Question C. Calculate the power the electrical device uses when the current is 1 amp. Well, formula for power. Formulas are your best friends. They make everything easy. There you go. When the current is 1 amp, check out the graph. They've even got the dotted lines for you. When the current is 1 amp, the voltage is 10 volts. Okay. Voltage is 10, current is 1, 10 watts. Put the units in the answer. Right? They'll take a mark off you if you don't put the units in the answer. Okay. That could have been megawatts or milliwatts or kilowatts. Tell them what it is. All right. That's question 4. Going to pause it for a second because I need to change the camera angle for what's next. Okay, question 3. Now this is the parallel circuit of question 3. We'll worry about the series one first, or worry about the series one later. And that tells you the answer to question A. Which of the circuits has the lights in a series arrangement? Circuit B is in series, circuit A is in parallel. It even looks parallel, right? It's got 3 parallel lines. A parallel circuit is a circuit where the electricity could go through one or another. It doesn't have to go through all of them. If you look at the other one, circuit B, it's only got one power line to go through, so the electricity has to go through the first light and then the second light and then the third light, so it takes its way through them in a series, one after the other, just like a TV series is one episode after the other. That's where they got the name from. All right, before we get into this, I just want to show you something. All of these other circuits are exactly the same as that, right? It doesn't matter what shape it is. What matters is the connections. In this circuit, electricity comes out of the battery, out of the cell, and it has a junction there, and it can go through one light and back to the battery. Keep in mind that that's what electricity is trying to do. There's a whole pile of electrons coming out of here. Right? If you can't remember which way it goes, that sort of makes an arrow. Right? And that shows you which direction the electrons are coming. So the electrons come out here and they could either go through that light to get around to the positive side, because this is the positive side of the battery, or they could go that way through the other one, or they could go this way through the other one. They're not going to do this. There's no point in electricity doing anything like that. All these electrons are trying to do is get back to the positive, right? It's like a long distance romance. It's like watching The Notebook with the volume down, right? So when they get here, having gone through here, they're going to turn left, right? There's no way they're going to sort of, tour the facility and, check out New Zealand along the way, right? They're just going to get to that spot as fast as they can. And when they all get here, they're going to suddenly notice that the road gets easier, because suddenly instead of one lane, they've got 2. And so they're going to split up, and they're going to split up there as well, right? Because that's the fastest way for all of them to get back to there, is to take many lanes and try to overtake each other, etc. Right? It's just natural. Now this one here, same deal. Electrons come out of here and they could either go through that light or they could go through that light, or they could go through that light. Keep in mind that these pictures are really sort of rigid, rectangular looking pictures of what are really floppy wires of metal, right? These can make any shape they want as long as the connections are the same. It really doesn't matter where everything is. It doesn't matter that that light's over there and this light's over there. It doesn't matter how long that wire and how short that wire is. That doesn't change anything, right? Same deal here. As long as you can say the same thing about the electricity, right? The electrons go out here and they could go through that light or through that light or through that light, right? Same with this one. This is literally this one with these two wires here disconnected and reconnected there, right? And it works exactly the same way, right? As long as you can say the same old story. It's getting boring now, right? The electricity goes around here, hits this spot, and it can go through one light or another, and then goes back to the positive side. So all of those circuits are actually the same, and they work the same. They'll have the same calculations about it, the same rules. All right. So I'm going to blow this one up because this is the one we were talking about. All right. Question 3, this is it. So this is circuit A, this is the parallel circuit, and part B says calculate the potential difference across each light globe in circuit A. Okay. A couple of people asked me about all of these different words that seem to be about voltage, right? There's voltage, there's potential difference, there's EMF. They are all the same. They all mean voltage, right? EMF stands for electromotive force. It happens to be the voltage that's produced by a motor, right? A motor produces a certain voltage of EMF, right? But it's the same thing, right? Potential difference is voltage that's used. So let me just sort of show you the story here. Electrons come out of here, going this way, with 12 volts of potential energy per coulomb, right? Voltage is how much energy each coulomb of electrons has, and 12 volts basically means 12 joules of potential energy per coulomb. And they're not going to lose any going through the wire. So they've still got 12, still got 12, still got 12. Right? They get here, some of them go this way, some of them go that way. But again, the wire isn't going to take any power from them. So they've still got 12 volts. Right? It's all going to get used. Right? By the time they go back to here, they've got no volts left. Now that's a bit of a rule of electricity. Whatever they've got, they're going to use it somewhere. Right? So if this is the full trip of these electrons, and there's only one thing that could possibly use any electricity, it's going to use all 12 volts. So they have 12 volts of potential energy there as they're heading for the light, and they've got nothing left here as they're going away from it. They've used all 12 volts there. Now when you measure voltage of something, when you get a voltmeter, you get one of those things that you plug in the wires and it's got the little meter on it. Beautiful drawing. This is how you connect a voltmeter. You do it in parallel. You don't put it in the circuit. You don't sort of stick it in there. That's wrong. Right? So you connect it there and it measures the difference in the potential energy from there and there. It's sort of a before and after, and it tells you what the difference is. And that's why voltage is sometimes called potential difference, because it's a difference between two potential energies, right? These electrons have got 12 volts of potential energy here. They got none there. So that used 12 volts. It just means voltage, okay? So all three of these things, EMF, volts, potential difference, they're all the same, right? One is produced, one is used, but it's all volts. Okay. So get back to the question. The potential energy, question B says, calculate the potential difference across each light globe in circuit A. Well, 12 volts, right? No matter which way we go, these electrons here that go this way are only going to go through that light. Right? I didn't go through another light. The electrons that take the top route, right, they're going to go through that light, right, the long way. So every electron that comes out of this battery is only going to go through one light. So it's going to use all 12 of its volts in whichever light it goes through. So the potential difference across the lights must be 12 volts. It's all got to go. Right, that's part B. Question C, it says, calculate the potential difference across each light globe in circuit B. I've got a circuit B here. Okay. B is a little different. That's a 12 volt cell. Excuse me. So the electrons come out here, heading around 12 volts, 12 volts, 12 volts. At this point, they've still got 12 volts. At this point, they've got no volts because they've used it all. These lights are going to use 4 volts each, assuming that they're identical lights. And I think the question said that, right? I'm just looking at the question there. 3 light globes. No, it didn't. Yeah, the light globes are identical and each light globe has a resistance of 4 ohms. Okay. So if they're identical light globes, they're going to take the same amount of potential energy as each other. So they're going to take 4 each. So if you've got one of those voltmeters, hooked it up, it'd say 4 there, it would say 4 across there, it would say 4 across there. If you put it across here, from there to there, it would say 8, right? Because 2 4s is 8. Now so the answer to question C is 4 volts, right? The question a lot of people ask me when I say this, that it has 12 volts there and this one's going to take 4 and that's going to take 4 and that's going to take 4. The obvious first question is, how the hell does this light globe know to only take 4 volts and leave the other 8 for these other 2 light globes? Well, it doesn't, right? It doesn't work that way. When you first connect this thing and the electrons start moving, keep in mind that this whole wire is already full of electrons. So this is like a garden hose that's already full of water from one end to the other, but the tap isn't turned on yet, or the tap is turned on and someone's got their thumb over the end, right? So when the electrons start moving from here, this light doesn't have to wait for them to get there because these electrons are pushing ahead of them, all of the electrons that are just sitting there in the wire, right? It's a bit like the full hose. Right? If a 30-meter hose is already full of water, then the instant you turn the tap on at one end, water is going to straight away come out the other end. You're not going to have to wait for it to travel 30 meters. Right? So all of this circuit fires up and starts rotating at once. And they've got some resistance there and some resistance there and some resistance there. And the electrons that are there and there and there, ready to just go through the lights, they all experience the same difficulty going through the lights at the same time, right? And all of that potential energy that's happening gets evenly divided from the first millisecond, right? So it isn't just that they know to sort of only take 4 and pass it on, right? It's a fact that the circuit is very evenly filled with electrons right at the start, and so they end up taking 4 and 4 and 4. All right, so that's the really long-winded answer to part C, calculate the potential difference of each light globe in circuit B. Okay, part D, calculate the current through one of the light globes in circuit A. Back to circuit A. Now you're going to use V equals IR. But one of the things about this, V equals IR only works if the V and the I and the R are for the same part of the circuit. So if you want to calculate the current here, you've got to know the voltage here and you've got to know the resistance here. Okay, so we're going to pick on this one because I've made a mess of that line, right? So, do we know the resistance here? Yeah, the question told us that each of these lights has a resistance of 4 ohms. So R is 4 for this little bit here. And we also know that the potential difference across that globe is 12 volts. We went through all that before, right? The electricity that goes through here has got 12, got 12, got 12, loses it all there, it's got 0. So the potential difference there is 12, right? So for that section, voltage is 12. Current we don't know. That's 4. Therefore, I is 12 divided by 4, which is 3. Now, I've got to pause this because I'm stopping a cat from walking on this piece of paper. There you go. No, no, he's off. Okay. So that was V equals IR for there. Right? So that's it. Now, part E, calculate the current through one of the light globes in circuit B. Okay, same deal, different diagram. Through one of the light globes, and again, one section. Actually, again, I've ruined that, so let's go over here. It has 4 ohms. We know that it's going to have a potential difference from there to there of 4 volts. V equals IR. 4 volts equals I times 4. I equals 1 amp. That's it. Okay? As long as you've got the V and the I and the R for the same place, right? That's fine. So we couldn't use the 12 volts there because that's for the battery. That's for the whole circuit, right? It's just here. This bit loses 4 volts. That's it. Okay. Question 5. I think that's the last part of that. Oh no, there's another one. There's 2 more. Calculate the power dissipated by a single globe in circuit B. Circuit B. Power. Again, VI. And again, look at this, the one place, okay? It says the power dissipated by a single globe. So don't do the whole thing. You're not using 12 volts. You're using the single globe. So the power dissipated by a single globe, right? It turns the electricity into light and heat, and it dissipates that, right? Dissipates just means spread it out. So 4 volts, 1 amp, 4 watts. That's a 4 watt globe. All right. Part G, in which circuit would the globes shine brighter? Now, voltage equals brightness in the case of globes, all right? These lights are getting 4 volts each. These suckers are getting 12 volts each. So these ones are going to shine brighter, right? That's why. So you firstly make the point that voltage is what determines the brightness of a light, right? And you therefore say, well, the lights that get the more volts get the more brightness, and that's circuit B. Sorry, circuit A. Ha! I knew that. You can't fool me. I'm a professional. Hang on a minute. Question 5. Now this takes a bit of reading. And it's about something that you've never heard of before, so it looks really scary because it's like 7 lines of reading, and it's about photovoltaic solar cells, which I've probably never said to you. So this is the sort of question that turns a lot of people off. Right? But don't be scared. Never be scared of a big word. Okay, photovoltaic solar cells, in other words, solar panels on a roof. They're being installed in houses throughout Australia, yada, yada, yada. Okay, a typical system creates 960 watts of power. Okay, let's just jot this stuff down, right? Power. We're going to need this. 960 watts. Here's the sort of magic list of stuff. Right? They generate DC electricity, which is converted, blah, blah, blah. In one set of these cells, each cell, that's a cell, I've drawn some, each cell generates 1.2 volts of DC power. So I've already got that up there, right? They're organized into a module that provides 12 volts of DC, right, with a current of 2 amps. So this is what I've done. A number of these modules, some unknown number, I could have drawn many more, right, are then organized into a parallel grid, right? I've drawn it parallel like those 3 light globes in the parallel circuit that provides 12 volts DC to the inverter. Okay, so we've got a rough idea of what's going on. Are the solar cells, these guys, that make up a module, series or parallel? Right. Voltage adds up in series. So in a series circuit, if you had that, and that's 12 volts, and then you put another one there, and that's 12 volts, that light is now getting 24 volts. Right? The electrons that come in here with no volts, they get another boost, and they've now got 12 volts. And then they're flying through here and they get another boost and they've got another 12 volts. So that's 24, right? Voltage adds up in series, right? So for these guys to ever add up to 12 volts, because they were 1.2 volts each, right? And a series of them was stuck in a module and it added up to 12 volts. That's what the question said. They've got to be in series, right? And there's got to be 10 of them because 10 times 1.2 is 12. That's what's going on. All right. So to answer the question, are they arranged in series or parallel, explain your answer. Firstly, answer the question. A lot of people put the explanation in and they don't put the answer, right? So the answer is they're arranged in series. Bang, got a mark, right? Then say why. Sources of voltage in series, whether it's a battery or a solar cell or anything, right? They add their voltages up if they're presented in series. That's the deal. Okay, part B, calculate the total current produced by all the modules when the photovoltaic solar cells are producing 960 watts with 12 volts DC. Okay, excuse me. Power is 960 watts. Voltage is 12 volts. Power was VI, right? Calculate the current. I is P divided by V, 960 divided by 12, and that's 80 amps. 80 amps of current. Okay. Part C. Sorry, I'm just scrolling on another computer up here where you can't see to look at the questions. Determine the number of modules. That's a module. Don't get confused. That's a cell, that's a module. Determine the number of modules that are arranged in parallel to produce that stuff. The answer is 40, and the reason for that is that this develops 2 amps. And we've just found out that the whole shebang develops 80 amps. Right? How many of these are you going to need to make 80 amps? 2 times 40 is 80, so you're going to need 40 of them. And they're going to be connected in parallel because current adds up in parallel. And that sort of makes sense. I'm going to get you another picture here. I'm going to very quickly draw another parallel circuit. Beautiful. Okay. If there's 3 amps coming out here, it makes sense that eventually one of them will go that way, one of them will go that way, and one of them will go that way, right? If all of these lights are the same, right? They'll split up because it's like a 1-lane highway opening up into a 3-lane highway, and they can do better. They can get back to where they're trying to go faster if they split up, all right? So current splits up, and of course back here, when they all get back together in one spot, they're going to add up again. 1 plus 1 plus 1 is going to be 3, right? So voltage adds up in series, right? So 12 volts, that's going to be 24. Current adds up together in parallel. So if you want more current, you put things in parallel and then join them all together. You force multiple lanes into one lane, and that adds the currents together, all right? So these guys, that module, and that module, and the next one, and the next one, and the next one, all 40 of them would be in parallel. And then they'd have all 40 of these lines coming together and getting all of those 2s adding up to 80. Okay. So calculate the maximum current. I did that, sorry, part D. Rightio. Calculate the maximum current available to the household when 12 volts DC is turned into 240 volts AC. Right, the amount of power is still the same, right? You're not going to change. This is the great constant. If this is developing 960 watts, that's 960 joules each second. That's not going to change. The sun isn't going to get brighter or duller, right? They told us this was in full sun. We're doing this whole thing in full sun. Right? So the power is going to be 960 watts. But now we've changed the voltage. The voltage is 240 volts. This is part D. I'm so glad I'm neat. This is part D. It said calculate the current. Okay, power equals VI. Same deal. It ends up being 960 divided by 240 instead of divided by 12. And that comes to 4 amps. Cool. All right. Final question, I think. Part E. Calculate the total kilowatt hours, what the hell, produced by the photovoltaic solar cells during 4 hours. Okay, I'm going to get a neater page here. Hang on. Getting sick of being messy. Spared no expense to make this. A whole new sheet of paper. Okay. Here's the deal. A kilowatt hour. When you use 1,000 watts for 1 hour, you have used 1 kilowatt hour of electricity. Right? If you didn't know that, fair enough. I understand. But this is how household electricity use is measured and charged. When you buy electricity from your electricity company, you buy it in kilowatt hours. Right? So they measure how many watts you're using and how many hours you've used it for, and they multiply those together, and that's what you have to pay for. All right. So in this particular case, the hours is 4 hours. So in this particular question, you've used 4 hours, and where are we? And it's a 960 watt system. So how many kilowatts is that? You divide it by 1,000. So it's 0.96 of 1,000. So that's how many kilowatts you're using, and that's how many hours you're using it for. So you multiply those two together. Right? A kilowatt hour, that's kilowatts times hours. Again, the units often tell you what the formula is. So it's power times time. Right? And again, they gave you a bit of a clue. Excuse me. No, they didn't. I thought they were going to say the word energy in the question, but they didn't even say that. Sorry, they didn't give you a clue. This is as good as you can get. So 0.96 times 4 was 3.84. Yes, 3.84 kilowatt hours. Question 5 was a very unfamiliar question. They had to read through the unfamiliarity and find out what you do know and still do what you can do. Not an easy thing. All right. Okay, my friends, that's it. Bye-bye.